So welcome to the today meeting. So our Non-Associative algebra seminar, weekly seminar. So it's my pleasure to present Michiel Smet from Ghent University, Belgium. Okay, so here I'm going to have a talk: cubic norm pairs and hermitian cubic norm structures. Welcome. Go ahead.
Okay, so thank you for the introduction. So I will talk about cubic norm pairs and Hermitian cubic norm structures. The reason that cubic norm pairs are in brackets is because I will talk a bit less about them. The focus will more be on Hermitian cubic norm structures. So first, I will recall different constructions of non-associative algebras that start from a certain class Jordan algebras. We will recall the construction of the algebras of type E7 and E8 that Freudenthal gave in the 50s. I will also recall the Tits-Cantor-Kröger construction for the algebras starting from Jordan algebras and introduce Q dimension 1 structurable algebras that come from Jordan algebras associated to cubic norm pairs. And these are, of course, three distinct constructions, but they are linked. So I will explain how they are linked. And after that, I will introduce Hermitian cubic norm structures and cubic norm pairs as a means to generalize these constructions. So first, I probably should introduce Jordan algebras. So most of this talk will be over a commutative unital ring R. So that's our base ring. And in Jordan algebra, over our ring R is precisely an algebra such that the product is commutative and a certain identity, as you can see on the slide, holds over all scalar extensions. The fact that this identity holds over all scalar extensions implies that other identities called delinearizations hold as well. And these other identities do not necessarily follow from this identity over R. The main example is an associative algebra where you just make the product commutative by taking the average of A times B and B times A. And this defines a Jordan algebra if 1/2 is contained in R. The second example, which is also interesting, is if you take an octonion algebra and consider the Hermitian 3 times 3 matrices of the octonions, and if you endow it with AB plus BA divided as 2 as product, then this will also form a Jordan algebra. This is an example of an Albert algebra. Albert algebras are forms of such H3 of an octonion algebra. And this example was maybe one of the original reasons to be interested in Jordan algebras. In the 30s, a German physicist called Jordan axiomatized these Jordan algebras because he thought that this might be an underlying structure for quantum mechanics. This didn't really work out, but of course I'm still talking about it. It's an interesting mathematical object, and quite a lot is known about these algebras. I will illustrate this by mentioning the classification. It's more to illustrate something than something we will really need. So there are three classes of simple Jordan algebras. Namely, I will start from below. Firstly, you have the Albert algebras, which are forms of H3 of the octonion algebra. We had the construction of a Jordan algebra starting from an associative algebra. If you do this for a simple associative algebra, you obtain a simple Jordan algebra. In case your associative algebra has an involution, you can look at the Hermitian elements. And these form a subalgebra of your Jordan algebra, and this algebra will be simple if your Jordan algebra is simple with respect to the involution. And then you have a third class where you start from a certain quadratic form. I won't go into detail. You can also, in case you have a scalar 1/2, think of them as subalgebras of a certain associative algebra with a product you made commutative. Namely, there you can embed it in some sort of Clifford algebra. Note that we made an assumption on R in our main example, and in this theorem we assumed that 1/2 was an element of our base ring. If you don't want to make that assumption, we should look at quadratic Jordan algebras. So I will define them now. I will explain how you can obtain a quadratic Jordan algebra from a linear Jordan algebra, and thereafter provide an axiomatization. So you first define the left multiplication operator, and then you can define the U operator from these left multiplication operators. And you can then use the linearization of U to define the V operator. So on the slide, you see two different ways to define V. The one is Ux, Z of Y. This is as the linearization of U. So Ux is quadratic in X. You can look at the linearization. And another way is in terms of these left multiplication operators. That's another way of defining the V operator. I will maybe illustrate these operators with the main example. If you have an associative algebra, Ux of Y is just xyx, and Vxy of Z is just a linearization of this Ux applied to Y. Okay. So what you can show is that J is a Jordan algebra if and only if these U and V operators satisfy three identities. You see the identities on the slide, and this is then precisely the axiomatization of a quadratic Jordan algebra. So you have a module J, a quadratic map U, and these equations have to hold over all scalar extensions. If that is the case, then you have a quadratic Jordan algebra. Okay. Now I will come back to the classification to illustrate that this really is the proper way of defining these algebras over arbitrary rings. Namely, we have the same classification as for linear Jordan algebras. For the rest of the talk, we will be mostly interested in degree 3 Jordan algebras, and even there we will be focusing on a specific subclass of degree 3 Jordan algebras. In order to introduce these algebras, I will first define cubic norm structures, and then I can define these Jordan algebras. So where do these come from? In the 50s, Freudenthal constructed real Lie algebras of type E7 and E8, starting from times 3 matrices over the octonions, over the real numbers. And he did this by making use of a certain cubic form. And this cubic form is more or less the determinant, though you have to be careful if you define the determinant on octonion matrices. Later, Springer characterized some pairings of cubic forms that lead to Jordan algebras. He did this over fields of characteristic different from 2 and 3. And this was inspired by what Freudenthal did with this cubic form. And ultimately, this led to McCrimmon defining cubic norm structures. And this is just a generalization of Springer's construction. And of course, here you should obtain a quadratic Jordan algebra. So now I will introduce these cubic norm structures. So you have a certain amount of maps. You have a cubic map N, a symmetric bilinear map T, and a quadratic map sharp. And being quadratic means that the polarization times, as you see on the slide, should be bilinear. Okay, so now you can define cubic norm structures. This means that two equations have to hold over all scalar extensions. You have a first equation, which links compositions of T and the sharp operator with linearizations of the cubic map N, and a second equation that links applying sharp multiple times to the norm. This is not enough. You need an additional element in J. I use 1 to denote this element because this will be the unit of the associated Jordan algebra. And for this unit element, you want that the norm of this element is 1, that 1 sharp is 1, and that a certain map defined from this unit element is the identity map. I will now give 2 examples. A first example is the 3 times 3 matrices over a base ring. Our norm or n should be the determinant. Sharp should be the adjoint. So the adjoint matrix is the matrix such that the adjoint matrix times the original matrix is the determinant of the matrix times the identity matrix, right? And we often use this name, the adjoint, for the sharp map. And the T map should be the trace form. So T of A comma B should be the trace of A times B. And these same maps, determinant, adjoint, and trace, work for the Hermitian 3 times 3 matrices over composition algebra C. So you should be careful with how you interpret the determinant. You have to define it the right way. And so, as I said before, a cubic norm structure defines a unital quadratic Jordan algebra J with unit 1. Yeah. To illustrate that these Jordan algebras have degree 3, and on the bottom of the slide, you see a generic minimal polynomial of degree 3. If you plug any x into this polynomial, you get 0. Of course, you have to be careful with how you define the powers of x. And in the way that the equation stands on the slide, it's not entirely sufficient to say that this Jordan algebra has generic degree 3, but I won't go into details for that. So now I will introduce the Tits-Cantor-Köcher construction, and later I will come back to Freudenthal's construction of the Lie algebras of type E7 and E8. So to define the Tits-Cantor-Köcher Lie algebra, we first define the inner structure algebra, and you do this by making use of the V operators for your Jordan algebra. Namely, you take the couples, Vxy comma minus Vyx as linear generators of a space of endomorphisms of J times J. And this forms a Lie algebra under the usual Lie algebra composition. And this is not a entirely standard construction of the inner structure algebra of the Jordan algebra, but it is equivalent to the more usual constructions. This is more in line with the construction of the inner derivation algebra for a Jordan pair, but this distinction does not really matter. Sometimes it's useful to add a so-called grading element, and this, if we do that, we denote this algebra with inner structure zeta of J. And this mostly does not matter. It does not matter if you have a scalar 1/2. If you don't have a scalar 1/2, it might be useful to add this element. So the Tits-Cantor-Köcher Lie algebra, TKK Lie algebra, is named after a certain construction of a Z-graded Lie algebra from a certain object, and that you can apply to a Jordan algebra. So you have a Z-graded Lie algebra. The 1 graded component and the -1 graded component are copies of your Jordan algebra, while the 0 graded component is your inner structure algebra. And if you want, you can add the grading element. I didn't write down all the possible brackets on this Lie algebra. I wrote the important ones. From this, you can derive everything. Namely, if you take a bracket of a 1 graded element and a -1 graded element, you need to use the V operators. and the inner structure algebra has a natural action on the one graded component and the minus one graded component.
Can I interrupt you? Okay, can you just repeat again? So what is G1 and G minus 1? Okay.
G1 and G minus 1 are distinct copies of your Jordan algebra. Yeah. And so your inner structure algebra is defined as pairs of endomorphisms of J, so you have a natural action on J1 times J minus 1. And for each one graded element, you can define an exponential. This is not really surprising if you have a scalar 1/2, namely the inner derivation associated to J is nilpotent of order 2. So if you have a scalar 1/2, the exponential makes perfect sense. And this will be an automorphism, provided you have a scalar 1/6. But since we're working with a quadratic Jordan algebra, you can define this exponential more generally, without any assumptions on the scalar. This will always be an automorphism. You can look at the group generated by these exponentials. The first one, if you only use the exponentials, is called the projective elementary group. You can look at the slightly more bigger group by letting automorphisms of your Jordan algebra act as grading preserving automorphisms of your Lie algebra. And this group is called the projective group associated to your Jordan algebra. To illustrate certain properties of this group, Lowes proved, though for a slightly different construction of these groups, as certain group sheaves. He proved that this projective group is a linear algebraic group if J is finite dimensional, that this projective group is semi-simple, if and only if J is separable, and that the identity component of this projective group is the projective elementary group. And here is a small remark that we will come back to later, is that these exponentials of one graded and minus one graded elements can be thought of as unipotent radicals of opposite parabolics. What do I mean by that? You have a Z-graded Lie algebra. This defines a certain co-character into your projective group of J. If PG of J is reductive, this defines parabolics, and from such a parabolic subgroup, you can obtain a unipotent radical. Okay, so now we can come back to Freudenthal's construction of certain Lie algebras. So you start from a cubic norm structure. So I will give a slightly more general version of Freudenthal's construction. You start from a cubic norm structure and define a certain module M, which is a direct sum of copies of R, your base ring, and your cubic norm structure J. And you can let the TKK Lie algebra Lj, or more precisely, a central extension of this Lie algebra, act on this module M. I won't give a precise description of this action, but you can define an action, and this action preserves certain maps, namely it preserves a quartic map Q and a certain Q bilinear map M. Later, in a different setting, I will give an action of the Lie algebra on M. For here, it's mostly important that it exists. And so Freudenthal did precisely this for R equals the real numbers and J 3 the octants. And the algebra preserving Q is of type E7 and is isomorphic to Lj. You can link this Q to the typical quartic map that E7 has to preserve on a certain module, but I won't go into details for that. And I will remark that this construction, you can axiomatize certain parts of it, and this leads to a notion of a Freudenthal triple system as introduced by Braun and Mayberg in the 70s. So for the construction of E8, you start you construct a Z divided by 2Z graded Lie algebra. You have a 0 graded component and a 1 graded component. Your 0 graded component is a direct sum of the central extension of your TKK Lie algebra, of which we used on the previous slide to define an action on the module M. And the other direct segment is SL2R, which has a natural action on R squared. If you have a direct sum of Lie algebras, you have an action on and one acting on one module, the other algebra acting on another module. The direct sum acts on the tensor product of both modules. This defines most brackets of this Lie algebra. If you want to be complete, you also need to define the bracket of L1 times L1 to L0, but I won't do that here. This is what Freudenthal did for R equals the real numbers and J equals to the usual algebra. And so one obtains a Lie algebra of type E8. Once again, this construction works for arbitrary cubic norm structures. And you can say a bit more about the gradings of this Lie algebra. As before, I said that we had a Z divided by 2Z grading of this Lie algebra. You can refine this grading into a Z grading, which is the grading you see on the left. So you split up your SL2R with respect to usual basis. H is your diagonal element. And then you can decompose your Lie algebra with respect in terms of eigenvalues of H. This is the grading on the left. Then you can use the Z grading of the TKK Lie algebra to obtain a second Z grading compatible with the original Z grading. So you have a Z squared grading, and the non-zero graded components form a G2 root system, as you can see on the right. So now I will go into structurable algebras, which will allow us to give a bit more details for Freudenthal's construction and the more general apply to a general cubic norm structure, and will also allow us to understand the Lie algebras once one obtains a bit better. So structurable algebras were introduced by Allison as a way to generalize Jordan algebras, and more specifically, the Titz-Cantor-Keuker construction for Jordan algebras. And as I said, these also provide new ways to understand Freudenthal's construction of these Lie algebras E7 and E8. For the definition, it's a definition that only works over fields of characteristic different from 2 and 3. You could try to define this more generally, but I won't. So you have an algebra with involution. Involutions means that the order of multiplication gets reversed. And you can define the V operator, and this is a generalization of the V operator for a Jordan algebra. And we call the algebra structurable if a certain identity holds. To reiterate the main point that this is a generalization of Jordan algebras, observe that if the involution is the identity, that this axiomatization is equivalent to being a linear Jordan algebra. So a linear Jordan algebra will be a structurable algebra with trivial involution. Conversely, a structurable algebra with trivial involution will be a Jordan algebra. So, as I said, you have a Keuker construction. I won't go into much details. You define an inner structure algebra. You can define it like this. I do it like this to stress the similarity with the Titz-Cantor-Keuker construction for a Jordan algebra. So you also need to define the skew elements, which are the elements such that if you take the conjugate, you add minus the element. And your Lie algebra is once again a Z-graded Lie algebra with on the 1 and -1 graded component distinct copies of your algebra. On the +2 and -2 graded component, you have the skew elements, distinct copies, and the 0 graded component, you have the inner structure algebra. You basically take the same Lie brackets you have in mind for the TKK construction of the Jordan algebra, and in order to make that work, you need to identify the skew elements with certain left multiplications. This characterizes the structurable algebras. I won't go into detail, but you can say precisely what kind of Lie algebra you obtain. And from such a Lie algebra, you can always reconstruct the structurable algebra. You can also link this to algebraic groups, as we did for Jordan algebras. Namely, if A is a central simple structurable algebra, you can look at the automorphism group of the Lie algebra. This will be an adjoint simple algebraic group. And you can also look at the identity component. And this group is generated by the exponentials of positively graded elements and exponentials of negatively graded elements. Similarly, as was the case for Jordan algebras, where you had the projective group of J and the projective elementary group, which was the identity component of the projective group. For the rest of the talk, we will be mostly interested in one specific class of structurable algebras, namely the skew dimension one structurable algebras, which are closely related to cubic norm structures. Namely, if you have a cubic norm structure, you can look at so-called matrix structurable algebras. These are algebras of two matrices. The diagonal elements are elements of the base ring, while the off-diagonal elements are elements of the cubic norm structure.
And the cubic norm structure you refer to McCrimmon, or definition?
What do you ask?
The cubic norm structure you refer to McCrimmon definition, the standard definition.
Yeah.
Okay.
Yeah. You can define a certain multiplication by making use of the t and times, which are part of the cubic norm structure definition. Note that there is a certain freedom, degree of freedom, this parameter eta, that appears in the multiplication. And this appears because there is some implicit pairing going on between the one copy of J and the second copy of J, which are off-diagonal. We also note that this construction actually also works for n equals 0 and sharp equals 0 and t arbitrary symmetric. I ask it here to be non-degenerate. Why? If t is non-degenerate, you will get a simple algebra. Freudenthal's construction of E8 can be thought of as taking the TKK Lie algebra of A with J and the algebra we already know so well. One theorem about skew dimension one structural algebras that says that they are somewhat understood is that if you have a skew dimension one structural algebra, you can take a quadratic field extension such that a tensor, this quadratic field extension, will be of either of the first form, so you can construct it from a cubic norm structure, or of the second form, you can construct it from a certain degenerate cubic norm structure with n equals 0. To understand these skew dimension one structural algebras better, so that you don't have to first look at the quadratic field extension, you can introduce Hermitian cubic norm structures. So we have our base field R, and we take a quadratic Itala extension with involution. So think of the diagonal subalgebra of the structurable algebra, of the matrix structurable algebra. We consider a K module J equipped with this A maps as a cubic norm structure. But now the interaction with the K scalar multiplication is a bit different. So sharp is not really a K quadratic map. It interacts using the involution with K scalar multiplication, and T now has not to be symmetric, but it has to be Hermitian. Now we call such a quadruple, so J with these maps, a Hermitian cubic norm structure if the same two identities as for cubic norm pairs hold over all scalar extensions. And note, before we assumed that we had a unit element 1, this assumption has disappeared, and it's more or less replaced by the assumption that the cubic map is non-zero. this works because there is an implicit pairing going on, but I won't go into details for that. So as before, you can define a structurable algebra. So A is K times J. K stands for the diagonal elements of your 2x2 matrix, and J stands for the off-diagonal elements of your matrix. And you can define a certain operation matching the operation of these diagonal and off-diagonal elements. And the involution is the involution of K, and you fix J. So this is a skew dimension 1 structurable algebra. And what you can show is that any skew dimension algebra such that A tensor E comes from a cubic norm structure after taking a quadratic field extension is isomorphic to an algebra coming from a Hermitian cubic norm structure. Okay, so I will now recapitulate the links between various objects we introduced, and thereafter I will introduce Hermitian cubic norm structures over arbitrary base rings. So Freudenthal, he gave a construction of a Lie algebra E8, starting from a certain algebra by first constructing a Freudenthal triple system on which the Lie algebra E7 acts. So this led to the notion of a cubic norm structure. And you can see that this construction of this Lie algebra E8 works for an arbitrary cubic norm structure. Namely, you have a cubic norm structure and you take the matrix structurable algebra associated to it. So the 2 times 2 matrices have we described before. And the other Lie algebra, so the E7, can be understood as the inner structure algebra of this matrix structurable algebra. Now, if you want to understand forms of these Lie algebras and structurable algebras, one just has to look at Hermitian cubic norm structures. And then one can describe a lot of forms of these algebras and the algebras. Okay, so what we will do now is introduce cubic norm pairs and Hermitian cubic norm structures, and I will formulate some goals in order to fixate what we will do. So the first goal should be to associate a structurable algebra and Lie algebra to such an object. There are scare quotes around structurable because I didn't provide a definition of such an algebra. You can think of it as an algebra for which the TKK construction we gave works. A second goal should be to define automorphisms of this Lie algebra, just as we were able to do for Jordan pairs. And we want to get some grip on the automorphism group generated by these automorphisms. One minor point, these generating subgroups should behave as unipotent radicals of opposite parabolics. I hinted at this before. I will come back to this on the final slide. So now I can define Hermitian cubic norm structures. And the idea is that we work over an arbitrary commutative unital base ring, and K should still be a quadratic Itala extension. And we have the same maps N, sharp, and T as before. And we will allow N equals 0 in order to understand both classes of skew dimension structurable algebras at the same time. So we have the same 2 equations as before. These are the 2 first equations. Then there are 2 additional equations, and we also have an equation for J to be well behaved. These additional equations don't matter if K is a field and N takes non-zero values. However, if K is not necessarily a field, these additional equations might become necessary. So I won't provide a full definition of cubic norm pairs, but the idea is that if K is split, so it's a split quadratic Itala extension, then we call J a split Hermitian cubic norm structure, and then you can split this Hermitian cubic norm structure into 2 parts, namely the idempotent T times J plus t bar, which is 1 minus t times j, and you can provide an axiomatization for this structure, which we call a cubic norm. So as before, we have a structurable algebra A, which is k plus j. You take the same multiplication as before, and you can obtain a Lie algebra, a Z-graded Lie algebra from that, and take some work to verify that this really is a Lie algebra, but it's quite doable. So now I will go into defining the automorphisms. I won't provide a full definition, but I will sketch how you define the automorphisms. First, you define on an abstract level the automorphism group, which is formed by pairs of elements in your algebra, and recall k times j is your structurable algebra. So you take pairs of elements in the structurable algebra, where the second element is determined by the first element up to a skew element, namely L plus L bar equals something determines L up to a skew element, and the second component lies in kj plus j star, lies in j, which remains fixed under the involution. So this is how you define the automorphism group on an abstract level. And for each x, y, and j plus, you can define an automorphism. And this x is the part, is the adjoint of, is related to the adjoint of x. So the +1 graded component of this exponential is the adjoint of x for the first component of g plus. And the other components, xy2, xy3, xy4, I won't define them at this point, and these act on in a certain way on the gradient. Now, to define these other parts of this exponential, it takes some work. If j is split, you have your z grading of your Lie algebra refines into a z squared grading, which you can use to define these exponentials on certain generators. And on those generators, it's relatively easy to define the exponential. If j is not split, you go around by first extending scalars so that j becomes split. Then you can use the easy definition of the exponentials, and then you can use a certain characterization of certain parts of these exponentials combined with the fact that it's an automorphism to see that the exponential of xy acts on the Lie algebra. I won't provide full definitions, but this is how you define them. You can do the same game for scalar extensions of this group, and for an analogous group which interacts x, y, I access plus y on the grading here. For g minus, you want that x, y, I access minus I on the grading. So now we come close to a sort of a sort of main theorem, namely if J is a well-behaved Hermitian cubic norm structure, and we look to a scalar extension L, we can look at the subgroup G of L generated by G plus of L and G minus of L, and these form a subgroup of the automorphisms of the Lie algebra extended by where the scalars are extended to L. You can recover the groups G plus L and G minus L by just looking at the bigger group and using the grading. Moreover, since G has a certain functorial definition, we can associate a certain Lie ring to G. And if you look at the commutator Lie subalgebra of Lie G, you recover the Lie algebra associated to the structurable algebra you obtain from J. For the interpretation of the result, it can be thought of as saying that G sigma and G minus are the resultant cycles of a parabolic. So once again, you have a Z grading on your Lie algebra. This defines some sort of co-character of the bigger group G, and provided that G is a reductive linear algebraic group, this means that you can define parabolics associated to the co-character, and then you recover G plus and G minus as unipotent radicals of these parabolic groups. And in some sense, this also characterizes Hermitian cubic norm structures in the sense that you can combine this unipotent radical condition with conditions on the groups G plus and G minus to characterize split Hermitian cubic norm structures. And I will explain this on the next slide in a special case. Namely, first, we will look at the algebraic group SL3 with a certain co-character. So co-character that's nothing more and nothing less than a morphism from the algebraic group formed by the invertible elements of the multiplication to your algebraic group. This defines a co-character. What do I mean by the parabolic group associated to lambda? This will be the upper diagonal matrices, and the unipotent radical of the upper diagonal matrices will be the upper diagonal matrices with ones on the diagonal. If you look at the lambda inverse of X, so just taking the group inverse, you can define an opposite parabolic, namely the lower diagonal, the lower triangular matrices, and the associated unipotent radical are the lower diagonal matrices with ones on the diagonal. So now we fix G to be an adjoint reductive algebraic group over a field. We take a morphism from H to G. We assume it to be non-trivial because otherwise some next assumption we will impose will be never satisfied. Namely, this co-character of H also defines a co-character of G by just using the composition with a non-trivial morphism, and you obtain opposite parabolics P lambda and P lambda inverse of G. And this is something you can do for reductive algebraic groups, and you have respective unipotent radicals G plus and G minus. The first assumption we make is that G is generated by these groups G plus and G minus. Okay. Now, we need some assumptions on these groups G plus and G minus. The first assumption is that these are smooth. This more or less says that the Lie algebra of G contains enough information about this algebraic group G plus and the algebraic group G minus. And this is what the smoothness assumption does. And we assume that these have weights 1 and 2 with respect to this co-character. So what do I mean by that? Lambda of X acts on a vector space as a certain, you can decompose the vector space into spaces for which that lambda of X acts as X to the power I. The subspace on which you act as X to the power I is said to have weight I. Okay, so we have weights 1 and 2, and we assume that two-weight space is one-dimensional. The remark between brackets is not entirely correct. It should not be it should not be the center of G plus. It should be the commutator of G plus with G plus, and this lies in the element of H because of this one-dimensionality assumption. I will maybe restate this a bit more in terms of the Lie algebra. So you have a Z-graded Lie algebra associated to your reductive algebraic group. And we assumed that only the two minus and minus 2 graded components are non-zero and the 2 and minus 2 gradient components are one-dimensional. So in some sense, behind the scenes, you can already see this Q dimension 1 structural algebra pop up, because we assumed the 2 and minus 2 graded spaces to be one-dimensional. So provided G is generated by G plus and G minus, that G plus and G minus are of this form, you can reconstruct G from a split Hermitian cubic norm structure. What do I mean by that? You take a split Hermitian cubic norm structure, you construct your structurable algebra, your Lie algebra, the groups G plus and G minus, and you look at the group generated by them. This group, provided you take the right group sheaf, will coincide with G. Slightly more generally, if you replace this H by a group of absolute type A2 but relative rank 1, this relative rank 1 is necessary to have a co-corrector. Well, if you have relative rank 1 or 2, you have such a co-corrector. In the case that you have relative rank 1, you will obtain that G can be constructed from a non-split Hermitian cubic norm structure. Okay. And yeah, so that's it.
You mean you're finished, right? Okay.
Yeah.
Okay. Thank you so much. Okay, so now it's time for comments and questions. So everybody will come. Okay. Maybe I can ask you in between. Okay, so I have a couple of stupid questions. The first is your slide when you several times point out that n equal to 0. N equal to 0 is allowed. Okay, so I won't understand. Okay, so what is the point here? Okay, so it was like the second, no, it's somewhere. Okay, so you wrote several items, and the second one was a sharp, double sharp identity, like X sharp. Yeah. Okay, so in that case,
this slide?
yeah, here A, this second one. Okay, in that case, if n is identically 0, well, what do you mean by n 0? It's identically 0, right? First.
Yeah.
Okay,
N is
so
identically equal to 0.
It will be the second sharp will be 0. Or what is interesting with n equal to 0? Okay, can you just comment on that?
It's maybe not super interesting, but by allowing this, we can understand all Q dimension 1 structurable algebras as grown from Hermitian cubic norm structures. But you're right, it's maybe not the most interesting case, but it's just useful to include it, to be as general as
it's
possible.
Not necessarily that you try to emphasize that we allowed because it leads to some specific construction, or so this n equal to 0. You also point out before that n equal to 0 gives some example. I don't remember what you really said, but okay. So I try to understand what does it mean this double sharp identity is equal to 0. Okay, so it doesn't recover the element as in classical sense.
Yeah, in some sense, the axioms become relatively trivial then. As long as you ask that sharp is 0 at the same time, then the only thing you ask is actually that T is a Hermitian form. But it's just useful to include these degenerate cases.
Okay. So a degenerate case or some radical case should be excluded or not. Okay, so it's interesting because I never thought about that. And in earlier, okay, but it's completely maybe a stupid question. So you mentioned E8 and L0, L1.
Yeah.
You remember there, okay. So yeah, yes, okay, here, okay. So this decomposition L0, L1, okay, of course it's not, but does there exist any connection or relation to vertex algebra setting,
Well,
or it doesn't, or you don't?
I've never thought about that. I'm not really
Okay,
specialist in vertex algebras or something.
no, okay. So it was no meaningless, okay. Jan, Seiden? Okay.
Yes, I have a question. Thank you for the talk. So in the end, when you looked at the algebraic groups constructions, you assumed some smoothness at some point.
Yeah.
Do you know how often is this? Like, do you have examples? I mean, so I assume these points are not in the SO3 case only; they are in general, or is this? My question basically in general is if you have looked at how like how often these groups are smooth, basically, if you can say something about when smoothness happens.
I have not really thought about that. The reason that I gave the characterization in this way is because then I don't have to precisely axiomatize what the underlying structure is we use for the characterization, because that's quite difficult. But if the main examples that come to mind are like, or the easiest examples are like Chevalier groups, and there, of course, it's there it's smooth. But of course, if you just, yeah, it's just to make an easy example. I don't really approach it that much from this angle. So yeah.
I see. Well, thank you. That was interesting.
Okay, let me just call. Okay, so do you have other questions or comments? Well, I don't see any. Okay, but let me thank you again, Michael. Okay, so for your interesting talk, actually, because it's really interesting, because these cubic norm activities were very interesting. Okay, so now our seminar is finished, and we are going to meet next week, next Monday. Thank you for all. Okay.